radians are standard. And whereas I think the metric system is stupid, radians make total complete sense. And it works really easy. It's something that I tend to really push you guys into the understanding of where it comes from and why it works and how it works. And generally speaking, as we get through probably about the second or third day of stuff like this, it's really easy. It just takes a little of getting used to what some of the terminology means. Okay? What I want to look at here to start with is just what does it mean to be in what we call a standard position. You asked for favors earlier in the week, doing stuff like that. That's a boat. So, we talked a little bit the other day when we were matching up angles, and I was showing you guys that shortcut for law of sines or for law of cosines when you wind up that ambiguous case. And we talked about what's called a standard position within the quadrants. What we do here is, if you have an angle in standard position, what happens is, this is what we call our theta, okay? This is called the terminal side. It's where the angle stops, if that makes sense. The terminal side of an angle could be placed within any of the four quadrants. It could be placed on what are called the quadrantals. The quadrantals are your axes. Okay, it's just a fancy name for them. They're quadrantal angles actually, because there's four angles, 90, 180, 270, 360. That's where they get that from. So what we can do here is talk about the terminal side of an angle, what quadrant it lands in. When we're measuring angles, to start with, we talk about positive or negative angles. When we're talking about positive angles, we always go in a counterclockwise rotation. We talk about negative angles, we go counterclockwise. You guys remember the quadrants, where they go? What's this one? 1. So we say Q1.
2, 3.
And then Q4. Okay. What you do here is you just kind of walk yourself through the graph, if you will. If you want to figure out what quadrant a 230-degree angle is in, well, you just place yourself on a grid, and to show where it is, what quadrant the terminal side lies in, as you come around. Well, 90, 180. Then how far off of 180 is 230? 50 degrees. So we come around, we come around and down, and it would be in quadrant 3. Remember we talked about what we're calling that reference angle? We talked about that a little bit when I was showing you guys why the values of sine were the same in two quadrants. You have what's called a reference angle. A reference angle is always how far an angle is bounced off the x-axis. It's always going to be a positive angle. So this has a reference angle of 50 degrees. Okay. That comes into play later on when we start talking about the trig functions of any angle. Not so much today, but as we're starting to build the idea of what a reference angle is. Just remember that it's always how far are you bouncing off of your x-axis. Okay. Does that make sense? Same idea if I'm spinning around the other direction. If I want to say I have a negative 135, where would that be placed and what would its reference angle look like? You're coming around. Now, you went all the way around. Do you go past this? No, because that's 180, right?
Yeah.
Okay. So we come around this way. We're in the third quadrant again. What would its reference angle be? How far off is 135 from 180? What is it? 45. It's just got a 45-degree reference angle. Okay. It doesn't matter whether you have a positive or a negative angle. to find the reference angle, it's still always going to be how far are you bounced off the x-axis. It works every time. Yeah.
The last example.
Yeah.
Put the 50 degrees
How far? Yeah, how far it was in here?
on the other side.
No, because that's the y-axis. Right. What happens, your reference angle is always how far you bounced off the x-axis. Okay? We're going to bounce everything off the x-axis. It's always going to be how far you're bouncing off those x-axis. All right, it's how far up and how far down. And the rationale behind that is kind of, you remember when we were talking about that shortcut for the ambiguous case? If you were up here, you came up here, these two angles were the same, therefore their y values were the same. That's why we were able to say that you could have that double triangle with that sine value, because you're bouncing your reference out off the x. Yes? It's just going in a different direction. It's not that it's a negative angle, it's just directionality. It's just showing that it's going another direction. That's all. That's all that means. It's like walking backwards. I'm still going a distance. The distance will be positive, but I'm just going in a different direction. Almost like a vector, if you will. What am I talking about? Okay. Does that make sense? It's just showing that it's going the other way. Because if you think about righty-tighty, lefty-loosey, for when you're working with screws and stuff like that, you can actually get into mechanics, and you're talking about direction of torque, and it can be just telling you the way that something is spinning. That's what all it is. Okay. Does that make sense?
Well, like, what are the angles that's what it's used in the
Yeah.
Would it just be like given in the problem?
Yeah, it's just going a different direction. That's all. Because what's going to happen here is eventually we're going to take stuff like this and we're going to graph that. And you can have positive and negative values of sine because it waves. And it depends on where your axis starts as far as where things are going. So you could have negative values of x for it to work. That's what's his name. Okay. Does that clear that out? Ah, sorry I was heavy. I just had to say it. Like I said, we talked about this standard terminal side. The terminal side is where it stops. The initial side is always at that 0 value. You don't hear much about that term very often. The book uses it. It'll say it's just always going to start at 0 degrees and work its way around. If you never write down initial side, it's not that big of a deal. Because we're always going to be looking at where the angle stops. We're going to look at the terminal side. Where does it end? Okay, we're going to be looking at that. When you go through these, well, we did this here. Let's, do we do 210? Let's do 210. When you spin 210, what quadrant does it lie in? Come around 180. And what would your reference angle be? Good, 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 good. So this is Q3. Geez, Roman numerals. With a 30-degree reference angle. Just kind of leading myself into what these reference angles are. The quicker you learn where the reference angle is, the faster the trig's going to be later on. What's that?
I don't know why it's just 30.
Well, if this is coming around, here's 90, 180, 210. When you go 210, you go past 180 degrees. How much past did you go? 30. How far is that terminal side off of 180? It's 30 degrees off. Yes, ma'am. Yeah. It's not. It's on an axis. It's a quadrantal. It's a quadrantal angle. Okay. And I'll show you that here in a second. Yeah.
So if it were to end the quadrant 2, what initial floor, like the side of the wall?
Okay, if you have a quadrant 2 problem, let's say, we'll just put it at 150 degrees, okay? You come over here, here's 150 degrees. How far are you off of the x-axis still? 30. So it's still how far have you bounced off? It's no matter what it is, it's how far are you bouncing off of the x-axis, whether you're above it or below it. It's still that same reference angle. Because the idea here is that these two wind up being in the same vertical position, therefore their cosines are the same when they have the same reference angle. Yeah.
The negative 45 one, the reference is 45.
Exactly. It's exactly right. Yes, sir. When we had here with the 45, the negative 45 degree angle, it's going down 45 degrees, which means its reference angle is 45 degrees. And it's in quadrant 4.
So
Okay?
if it was negative 50, would the reference angle just be 50 then?
Yes, because it's how far is it off of it? It's 50 degrees off, okay? All right.
It makes sense.
Now, the last one here is 510. I'm going to put it on a different sheet so we have a little bit of space.
510.
You didn't know they stack stuff that high? Now, here's where you have to be careful. We go around, that's 360 degrees, correct? Now, what's 360 plus 180?
540.
540, so it's got to be over here somewhere, right? So how far off is it? It's 30 degrees off. So the reference angle is 30. So it's in Q2. You're going to see these where they're going to spin themselves around because no matter what, as you continually spin around the axis, it's just going to go, 360, 720, 900. No. Wait. 1080, yeah. Excuse me. Math is hard. Yes, sir.
So the reference angle is always to the x-axis.
Always to the x-axis. The reference angle is always going to be how far you bounced off the x-axis, whether it's above it or below it. It's always that bounce. Okay. Reference angle will always be positive as well.
That's
Right.
the angle we use in science.
Yeah. And that's kind of what we always do.
Okay.
All right. Here's the thing with this 510 then. What happens is you can get what are called coterminal angles. Coterminal angles are going to be angles that have the exact same ending spot, but different degree measures. Think about this. If it has a 30-degree reference angle in quadrant 2, very good. The other angle that has that exact same terminal spot would be 150.
Does there always work that you can just switch it over?
Dumb luck. It's dumb luck, okay? 500 and the other one would be 160. Okay. It's just so happened to be dumb luck that happened. Now, what happens here is that this is called a coterminal angle. Coterminal angles are just angles that have the same ending spot within the same quadrant. They're usually found by adding or subtracting 360 degrees. Notice that if I subtract 360, what do I get? 150. I unspun it. I came back around, right? It works the same way. What else? Scrunchy face.
Yeah, because I'm thinking of
I'm going to show you negatives here in a second. I'm going to show you that,
That's
okay?
why.
It's okay. Don't worry so much yet. It's not as fuzzy as it sounds. Mike. No, it's just dumb luck. It's dumb luck because of where the reference angle bounces to, okay? You always are going to do multiples of 360, okay? Now, when we're dealing with these reference angles, they're called coterminal. The angles that are coterminal with any given angle can be found by adding or subtracting multiples of 360 degrees because you're unwinding it or you're adding to it to come back around, all right? What happens a lot of times is that we're going to list out one positive and one negative coterminal angle. And that means sometimes you'll have to subtract 360 twice. Sometimes you have to add 360. It just depends on what you start with. For example, if we did this one where we had 510, And we wrote that one out already, that our first coterminal angle was 150. We spun it around. We wound up in the second quadrant. If we subtract 360, we wound up with 150 being its positive coterminal angle. If I subtract 360 again, I'm going to get a negative angle, aren't I? Which is how much? Negative 210. That just means that going the other direction, 210 degrees, it also has the exact same coterminal side. Does that make sense? You're just going both directions. You're going to find one positive ending spot and then one negative. So all you had to do here to get both of those, since 510 was already more than one revolution, one time around the circle, you just had to back it up twice. Okay? This was really quite simple when you start to do a few of them. I know you were worried about the negatives, but does that make sense where I'm getting that negative? I'll show you another one. Let's look at negative 60 degrees, and then we'll do one at 495. Let's do the negative 60 first. We're going to find a positive and a negative coterminal angle at negative 60 degrees. Okay? Excuse me. If I wanted to find a positive coterminal angle to it, what would I have to do to the negative 60? Add 360. So if I add 360 to this, I'm going to go, where am I now? 300 degrees. Coming back around, I'm at my 300 degrees. There's my positive. Now, how do I get another negative? Subtract 360. What do you get? Negative 420 degrees. That's all you're doing. You're adding or you're subtracting 360 degrees to get another positive or another negative to get to be within the same position with that same terminal side. Does that make sense?
So when you're given a negative 60,
That's your terminal. That's going to say it has an angle measure of negative 60. How do they write it out? Yeah, they're just saying find a coterminal angle of negative 60. So negative 60 just tells you to start at 0, go down 60 degrees. So if you're already given a negative, you add 360 to that, and you subtract 360. Those are your two angles. All right. At 4, come on.
But isn't, never mind.
At 495, it's a deal. It's 495. 495. What quadrant do you wind up in? There's 360. So I have to go up another 135 then, correct? So I'm the second quadrant. Okay. So at 495, to start with, do I have to add 360 to find the next one, or do I subtract it to find the next one? Subtract. Since I'm over one revolution, my coterminal, I need to subtract. I want to bring it down to the next value. It's at 135. There's my positive. Bring it down another 360.
number, and then you have a negative.
Negative 225.
Yeah.
And you know why that is? What's the reference angle off of 135? It's 45 degrees, right? If I go this way, it's negative 180. Add a 45, you're at negative 225. So those are your two coterminal angles. It really does get that fast by seeing how far things are bouncing off axes to get that reference angle. The reference angle is going to be where it's at. Yes, ma'am?
So why
It helps us to, when you're dealing with larger angles, when you find the coterminal angle, the trig becomes easier.
Okay.
Because right now, I'm seeing that I'm going to be dealing with a 45-degree reference angle. And I know what the sine of 45 is, I know what the cosine of 45 is, and I know what the tangent of 45 is because we've done that with our special right triangles. And that's where all of this is built on. Yes, ma'am?
Especially when we have to do this, but like, if you have a 90-degree angle and you find that one of the other angles is 30, and Is there any way to try these because it's like 36 to 90
Of doing law of science stuff?
I guess.
I don't think so. There is no, I don't believe there's ever been, that I know of, that you can get an ambiguous case with the 90-degree angle, because once you get the 90-degree angle, it becomes set that you've got the Pythagorean theorem. Because there isn't going to be two, if you have two side lengths with the Pythagorean theorem, you have to get that third. It's not going to be any wavering on it.
Okay. I don't know why.
I don't know. No one's ever asked me that. I honestly don't know. I honestly don't know.
Okay.
Okay. That leads us to the dark side, if you will. Radians. Radians are dealt with in terms of what we call a circle. Okay.
Should we draw that?
We'll draw something here in a second. What I want you to notice when you're dealing with the circle, the one thing that stays constant within the circle is the radius. You agree?
Yes.
The radian is the measure that something is moving around this outer edge of the circle. What's the outer edge of a circle called?
Circumference.
Circumference. How do you find the edge?
No, she said positive.
Oh,
2 pi r.
it's 2 pi r, right? So here's what happens. When you have what we're going to call our unit circle, I'm going to try and do this cleanly here.
Cheater.
Yeah, well, you're going to have to deal with it. I've had a really bad day. I'm allowed to do something.
Also,
Technology is helpful. Let's label this out to start with. You know what? Let me get this on a larger slide so you have a little bit more space. It's close enough. All right. This is 0. You agree? This is 90 degrees. What's this?
180.
180. I really wish the smart board would write. It's kind of annoying. This is,
270.
and then when I come back up to here, we get to 360. Good. Now, if the circumference of a circle is 2 pi times the radius, if I say that my radius is 1, what's my circumference? 2 pi. So my radius is 1. Therefore, my circumference is, so 360 equals 2 pi in terms of radians. Okay. If I go to 180 degrees is half the circle, correct?
1.
So just 1 pi, just pi. Good.
It's just pi.
So it's 1 pi for 180.
Correct. You don't have to put the 1 in front. You don't need to do that. It's not a big deal.
Is it half a pi at 90?
It is half pi at 90. Good. So we write it as pi over 2.
Oh, okay. I didn't know.
All right, we'll write it as pi over 2. Well, isn't this halfway between 1 and 2?
Yes, it is.
What's halfway between 1 and 2?
1 half.
1.5 pi, so it's 3 pi over 2. We don't use mixed numbers, 1.5 pi. This is Russia. No, we say 3 pi over 2. Yes, ma'am.
Okay, so if we were doing one that's like 510, we have to multiply these like twice? This is way more.
Isn't there, are there a bunch in between we have to know?
Oh, there's really 3 of them in between each one of those. And what do you think they're built off of?
36 to 90.
30, 60, 90, 45, 45, 90. Basically, you're going to find a clock. You're going to work with a 30-degree angle, 45-degree angle, and a 60-degree angle. Because notice what happens. When this comes over here, it's got the same reference angle. When this comes over here, it's got the same reference angle. All of those 3 special angles wind up with the same reference angle within all 3 quadrants. The only thing that changes for them will be their sign, S-I-G-N, whether it's positive or negative, depending upon what quadrant you lie in. This is really quite easy to build itself out of, okay? Now, when we do this, there is I'll come back to this of how we build the rest of the triangle up. I'm going to show you the generic formula for converting degrees to radians and radians to degrees. To go from degrees to radians, you multiply by pi and divide by 180. To go the other way, you multiply by 180 and divide by pi. So Izzy, you were worrying about 510.
Yeah.
If you wanted to go 510 degrees into radians, you slap a pi next to it and you divide by 180. Simplify your fractions. Okay? So 3 goes into 51, so it goes 117 pi over 6.
Yeah, up there, like in the green box.
Radians is in terms of pi. You know that button on your calculator that's rad?
Yeah.
That's what that stands for. It stands for radians.
It's so rad.
Because radians are in terms of the unit circle, which is dealt with in terms of pi, whereas degrees are dealt with degrees. Radians converts degrees, excuse me, radians are the decimal value of this.
Not finding a rad.
So how can you have radians in the conversion here going from degrees?
To convert from degrees, if you go long form, like you guys are used to seeing, what is that, dimensional analysis, I believe it's called? When you're multiplying stuff out, converting units. I think it's called dimensional analysis. What happens if you're starting out with 510 degrees, and I'm multiplying that by pi radians over 180 degrees. Notice how the degrees are canceling out?
Yeah.
That's what it is. It's converting inches to feet. It's the same idea. What is it? Yes. Yep. You don't have to write 17 pi over 6 radians. Once you put it in terms of pi, it is implied that you're in radians. What do you got?
So, I'm basically just asking the same thing. So you just put 5 to pi over 180, and you
Yeah.
put r80
Nope.
in there.
Don't need it.
So what does that use for?
We'll get to the calculator later. A lot of this stuff in terms of radians, you don't use your calculator for a lot of this. Right now, it's just a matter of simplifying a fraction. This is it.
So you did like the 5 times symbol going from degree to radian. Can you just example that?
I'm getting there. I'm getting there. Let's look at this one. 110 to radians.
What does that mean?
I'm going from 110 degrees to radians.
Yeah.
Slap a pi next to it. Put it over 180.
Yeah.
Okay.
Yeah.
11 pi over 18.
Yep.
Right.
Ooh, that's what I thought. Also, the 11 and the pi look very much the same on my
Now here's the deal. If you're really worried that you don't know how to simplify a fraction, could you type in 110 over 180, hit math, enter, enter, and it'll tell you what the simplified fraction is?
Wait, does that?
It does that. Slap a pi next to it then. It won't do it, your calculator will not keep your units in terms of pi with the fractions. I believe the old multi-views that you used last year, I think those did. But multi-views are pretty stinking cool.
Enter, enter.
Oops.
It worked. Yay. Our math teacher was right.
Go figure, your math teacher has half a clue every once in a while, right? As hard as it may seem to be.
Also, you said slap a pie next to it so many times. I think
Well, slapping a pie next to it is just kind of
the
the-
only right thing to do would be to open up
What
a
about
pie
a sheet
shop
of pie?
with that as the slogan.
Going the other direction, going from radians to degrees. One of the things you'll notice is that this book always tends to put the negative, when there's a negative a lot of times with fractions, it usually lines it up with just the fraction bar. It doesn't matter where you place it. I usually put it in the numerator, so that way I know it's there. You have negative pi over 9. Now, if I want to go from radians to degrees, I'm going to multiply by 180, divide by pi.
I was confused at the pi.
Those are 2 minus 11.
Yeah, I
Yeah.
thought it was minus 11 too.
I got you.
All right.
I get
What
that.
happens to the pi's? The
They-
pi's drop out. You get negative 180 over 9.
Which is negative 20.
Okay.
Wait, are you multiplying it by 180 over 5 because that equals 1?
Yeah. You're trying to get rid of the pi, and that's how your pi drops out. Whereas the other one, you're multiplying by your degree, you're dividing by degrees to get the degrees to drop out. It's that whole idea of being able to use what we call dimensional analysis, and it's unit conversions. Is really all this is. Okay, it's a really fast unit conversion. Okay.
So the 110 radians, you said about 110 and the 180 cancel out?
They don't cancel, the zeros drop out. It's 11 over 18. Yeah. Here, I apologize. I didn't rewrite that out to be 11 pi,
Seriously?
Oh, that's nice.
and that's a simplified fraction.
Thank you.
All right.
Yeah, I know. Yeah.
Homework. What I will do tomorrow. Wait. I know.
Memorize this thing.
You don't need to memorize it. The reason you don't need to memorize it is because this quadrant is replicated.
Oh, okay.
All right. So just to start with, go back to the circle that we did with that. We're going to put in the radian measures for a 30, 45, and a 60, and just kind of, I'm going to show you guys how these things bounce themselves around. We have this at 0. This was pi. This was 2 pi. This was pi over 2. And this was 3 pi over 2. We okay on that? We already had that written down. I'm going to go, the first angle is going to be 30 degrees. If I say this is 30 degrees, if I convert that into radians, I slap a pi next to it and divide it by 180. So I get 30 pi over 180, which is
Well, pi over 6.
pi over 6. Yeah, 1/6 pi, yeah. What we write in is just pi over 6. So you get pi over 6. All right? Do that with 45. When you do that with 45, you get pi over 4. Because think of it this way. If 90 degrees is at pi over 2, what's half of 90? Pi over 4. Because half of a half is a fourth. So that's where you get pi over 4. Bless you.
Pi over 6.
What's that? For what? And then if I do 60 degrees, I get 60 pi over 180, which is pi over 3. Use the formula. Multiply by pi, divide by 180. Okay? Now, here's what I want to show you real fast in terms of reference angle. If you have a 30-degree reference angle off of one side here, that means that this is at 150 degrees. You guys agree on that? Okay. Now, if I think about in terms of pi, isn't that going up pi over 6? It's going up pi over 6. So if this is pi, and I subtract a pi over 6,
It's 5 pi over 6.
it's 5 pi over 6. So did I have to memorize that? No, because it's in the same reference angle. If I start at pi and I have to go up pi over 4, I took a quarter out. So I'm at?
3 pi.
Perfect. I'm at 3 pi over 4. I'm moving it up. Okay? It's the same reference angle. If I came up pi over 3 off of pi, what am I left with? 2 pi over 3.
I understand the difference, but like,
What I'm doing here, think of it in terms of
So
fractions.
it's a whole and then you just subtract.
The part. Yeah. Pi is 1 over 1. Okay? If I say that this is 1 over 1, can I say it's also 6 over 6?
Yeah.
What's 1/6, or excuse me, 6 over 6 minus 1/6? 5/6. If this is 1, Can I also say it's 4 over 4? Subtract a fourth, you're at?
3/4.
3/5.
And if I say this is 3 over 3, it's still 1, isn't it?
Yeah.
Subtract 1/3 and you're at 2 pi over 3. It bounces itself off of that each time. You don't need to memorize it. There's no need. As long as you know pi over 6, pi over 4, pi over 3, everything bounces. Everything bounces off with that reference angle. Okay? Everything moves itself down. Think of it in terms of, yeah.
So for 270, would it be 3/2 minus 1/6?
Don't, because you're bouncing off the y-axis. Remember, bounce off the x.
Oh, okay.
Bounce off your x-axis. So if I go here, I'm moving down another pi over 6, because it's 30 degrees.
It's 7.
Exactly. So this is 7 pi over 6. I move down a quarter. 5/4. Very good. I move down a third. 4/3.
So swing about 2-ish.
There's a couple of patterns that you might pick out on these things. I don't want to get too involved in the pattern. Because if you know the first quadrant, and you know how to subtract or add, everything just moves itself around. Okay? Now, if I'm going to the fourth quadrant, then using those same reference angles, 2 pi. It's the same thing as saying 12 pi over 6. Is that okay? So if I move down to 6, I'm at
11 pi.
11 pi over 6.
Okay.
I'm thinking in terms of fractions. Izzy, what's wrong?
I don't understand what you're doing that.
All right, Izzy, 2. Get rid of the pi. I want to subtract 1/4 from 2. Can I say that 2 is also the same thing as 8 over 4? What's 8 over 4 minus 1/4? So there you go. 7 pi over 4. I don't have a 2 there, Izzy.
No, but you said, like,
This is 2 pi.
okay.
So I just got rid of the pi for right now, so it's 2. Rewrite it as a fraction. 8 over 4.
Why are you subtracting?
Reference angle. I'm coming off the reference angle coming down.
This is
It's- It is, it's nuts, isn't it?
Wait, so the reference
Yeah.
angle is 1/4?
Yeah.
Okay.
I'm bouncing it off the x-axis. I came down a quarter. 1/4 pi. That's where I'm coming with. I just didn't say pi so she could see where I was coming from.
Look at the big picture.
These are all built on the same thing.
Oh, that is
These literally, guys, this is a great question. Every one of these, this is up 30 degrees, this is up 30 degrees, this is down 30 degrees, this is down 30 degrees. They have all the exact same reference angles. If you notice what's going to happen here, oh, let's get this last coordinate in first, and then I'll show you this trick here. What was it? 5/3, good. So it's 5 pi. What's going to happen, and this is going to really blow your mind here, more so probably already going now. From here to here, same y value, right?
Yeah.
Okay? From here to here, it's the same x value. From here to here, it's the same y value. And from here to here, it's the same.
It's a rectangle.
It's a rectangle.
And the 45 is square.
And this, what happens here, in quadrant 1, both values are what? Positive. So x and y are both positive. Oops, are both positive. Here they are negative and positive. And we talked about this earlier. The y value in the second quadrant is your what? Sine. Remember that? The y values are sine.
Yeah.
They have the same positive value here. Down here, they're both
Negative.
same cosine value. Over here, we are positive and negative. So between these two, they have the same cosine again. And this, every single one of these problems is built off of these 3 angles. As we get into this, these 3 angles will give us our x and y values, our cosine and our sine values that are mirrored within all 4 quadrants with different sign SIGN. That's it.
So you just have to find,
Then you have to calculate.
so you just got
As we build into more of this stuff, it's just gonna be all off.
You make like
And you'll have to do coterminality.
Yeah.
Is it only?
Great question, real quick, just one second. She said, what happens if you're not given a 30, 60, or 90? Well, if it's not one that has a coterminal angle of one of these three, you're screwed, you gotta use a calculator. But most of the ones that we build into this, they're all gonna have a reference angle of a 30, 45, or a 60 as you build through. Let me give you a couple, just to switch it around. Yes, ma'am?
Me?
Yeah.
Oh, so, if you have one, like, 40,
Yep. Without doing any work. Mike?
Can you explain how to get, like, 11 pi over 6? You subtract it by 1.
Pi over 6. Because I went 11 pi over 6, it has the same reference angle as this, pi over 6. So 2 is the same thing as 12 over 6. 12 over 6 minus 1/6 is 11/6. I just moved it down.
You can make different shapes besides a rectangle.
No, not really. Let's do this. We'll build, I'm going to give you guys a blank one of these tomorrow. We'll build more into that. Let's see here. So this is 13.2. We'll start at 32. We'll do 32 through 58 evens. We'll start with that. There's more stuff that we can do in this section, but I want to really overemphasize the simplicity that really is within finding coterminality and how you are able to find those reference angles. Okay?
Are we gonna do some of these tomorrow?
I don't know if I'll be on that. I probably will be, but I don't know. It really depends if we can find someone for our dog. So, questions?
I'll take it.
Thank you, Michael. Yeah.
So this one's back here.
Yes, Michael.